So in this video, we're going to look at using a table to do integration by parts. Now, the tabular method for integration by parts is really useful when it works, particularly if you have to do a lot of steps in the process, but it doesn't work all of the time. So there are some caveats that have to be discussed first. So the integration by parts works in the tabular method particularly well when u is a polynomial. And that's going to come up quite frequently. And so it is an extremely useful technique, even though it applies to a very limited set of functions. But if u is a polynomial, the thing about u is that as you differentiate each time, the function will get simpler until eventually it disappears. It becomes exactly zero. And that is exactly what we need in order to do the tabular method. For the dv portion of the function, this can be another algebraic function. It can be a trig function, or it can be an exponential function. The key for dv is that it has to be a function which can be integrated on its own, so that it doesn't need to borrow, and nothing is going to simplify in the intermediate process. So this is one of the reasons why the log and inverse trig functions don't work here, because in order for them to actually go anywhere, their derivatives are not going to actually end in a zero at some point, and they're going to interact with whatever the dv results in the cases where it can be simplified, and that interaction can't really be captured in the table. For other kinds of algebraic functions, again, they're never half power, fractional powers, or negative powers. They're never going to end. They're never going to disappear. And same thing for sine and things like that. They loop around, they change, but they don't disappear. And so they don't really work particularly well with tabular method. So if u is a polynomial, and if you have to do integration by parts more than one time, then the table can be extremely handy. But again, we saw an example with a polynomial combined with an exponential in a previous example, and we had to do u substitution to integrate our exponential function. That kind of a situation is not going to work in the tabular method. For something like that, even if you have to do it a bunch of times, you're going to have to literally do it a bunch of times. But in this particular scenario, we have e to the 2x. E to the 2x is just it is a composite function, but it just produces an extra constant, an extra coefficient each time we integrate. And so it can be integrated by itself. And then we have x to the 5th, and x to the 5th, this is telling us we're actually going to need to do integration by parts 5 times if we do it by hand. 6 different integral steps, because we have to finish out the last one. So it's a lot of integrating. And so in order to avoid that, in order to avoid manually doing all of these u and dv selections, the tabular method is going to work really well in this. So you're going to build your table. Now, every time you do an integration by parts step, remember there's a minus sign in there. And so when you start stringing together minus, minus, minuses, the signs will flip. So we have one column that represents just the sign change. The UV starts out positive, then the next one will be negative, and so forth. The U column, you place your selection for U for your first choice. And then what you're going to do is you're going to differentiate this going down the column until you run out. And that's why it needs to be a polynomial. So we started with x to the 5th, and the derivative of that is 5x to the 4th, and the derivative of that is 20x cubed, and the derivative of that is 60x squared, and the derivative of that is 120x, and the derivative of that is 120, and then the derivative of a constant is 0, and that 0 tells you how long your table has to be. That tells you when to quit. Now, the dv column is, again, it's going to be, in this case, the exponential function. And every time you do integration by parts, you have to integrate what you said dv was going to be. So that's what we're going to do. Going down this table, we're going to do the antiderivative of our dv function. So the antiderivative of e to the 2x is 1/2 e to the 2x. And then the antiderivative of that is gets another half, so that becomes 1/4 e to the 2x, and then 1/8 e to the 2x, and then 1/16 e to the 2x. And again, you keep going until you get to the row where the 0 was. Now, the way that this tabular method is going to work is you need to combine a u with a v. And so the v is the antiderivative of your original dv. So this is u, and you're going to combine that, multiply it with the next row down from your original u dv selection. And the sign on the line with the u goes with it. So positive 1/2 x to the 5th e to the 2x. And then the next line down, you take the negative 5x to the 4th times 1/4 e to the 2x. And then, because now it's a minus minus, it's a plus again, 20x cubed times 1/8 e to the 2x. And you keep combining on these diagonally on these rows until, again, you get to the 0, because you even if you were to keep integrating, you're now multiplying by 0 all the time. So your last step is right above the 0, in this case minus 120 times 1/64 e to the 2x. And if you do the simplifying with the coefficients, 5/1/4, and then you had 20/1/8, so the 4's canceled. Then you had 60/16, so you had a 4 cancel, and 60 divided by 4 is 15. And then here 120/32, again, you're going to have, in this case, an 8 that's going to cancel. And then 120/64, an 8's also going to cancel, but you're going to be left with 15/8. And then you just string together all of these plus, minus, plus, minus, plus, minus. And when you get to the last line, then you just tack on your plus C. This is very efficient. I have known math professors who teach integration by parts, who teach Calc 2 on a regular basis, who can do this in their heads, which I've been teaching math for 20 years, and it takes me much longer to do this in my head than it takes him. So it can be extremely, extremely useful when you have these problems that you have to do multiple times. Honestly, if you have to do it more than twice, I would recommend, if you can, to use this method. But again, it is a very limited, restricted method, but these polynomial times exponential functions or polynomial times trig functions actually come up fairly routinely in applications like physics. I remember seeing quite a few of them in quantum mechanics, for instance. And so they can actually, even though it's very limited in application, it applies to things that show up very, very frequently.